The year was 1998. U.S. President Bill Clinton was 1 year into his second term when the scandal that would overshadow his presidency broke. He was set to stand before a grand jury and testify, and the nation was set to watch, some on their huge cathode ray tube computers, with a little help from the World Wide Web. A few months later, on February 5th, 1999, the Victoria's Secret fashion show took the same approach, deciding this would be the very first year they would broadcast the show over the web. It accrued 1.5 million viewers. The rush to online video began. Webcasted events exploded in popularity. Consumers were hungry for internet video. There was just one problem. Streaming video in the late 1990s was an excruciating experience.
Think about trying to watch a video where you're getting maybe one frame every 2 or 3 seconds and it's the size of a postage stamp. No joke. I mean, that's how small the window was, and it didn't work very well. Too many people tuned in. There wasn't enough infrastructure capacity in place at the time.
Streaming couldn't be a mainstream tool until these major quality hurdles could be overcome. And that wouldn't be possible until the groundbreaking introduction of the CDN. This is the Lightbulb moment, a Cheddar and Curiosity Stream original series, the show that uncovers the surprising impact of less celebrated inventions and the moments of inspiration that made them possible. Though we like to think of the internet as a nebulous cloud floating above, it's much more physical than we give it credit for. And in the early days, the physical limits of the internet were inescapable. If too many people visited a website at the same time, congestion would overwhelm the servers. Then there was the issue of geography. The internet is a network of networks. If you're trying to retrieve packets of information, like a web page, and its servers are located geographically far away from you, your computer has to send out a request that travels through different layers of the interconnected chain to retrieve that web page. Once that request is received, the server can approve the request and start sending individual packets back through the chain. These packets have to travel the same long distance from the server back to your computer. Though it's not always the defining factor, generally speaking, the farther away a server is, the longer it takes to retrieve the packets that make up a web page, which for a consumer means longer loading times. This worked okay for static web pages, but for any large file, it was going to be a problem. And video required some heavy lifting. In 1995, streaming video was a dream at best. The internet just wasn't built for it.
Back then, object sizes on the internet were very, 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 very small. There was no video, there was no software downloads, there was no Call of Duty patches that are gigantic. It was all JPEGs, it was GIFs. Maybe it was JavaScript or it was some HTML code. It was very, very small objects.
Video, by comparison, is massive. A short video clip could be 1,000 times the size of a photo or more. Because of this, streaming video struggled to become mainstream in the 90s. At the time, the best way to transfer video was to host the file on a server and have the recipient spend a substantial amount of time downloading it.
When it came to downloading videos, many times that was done simply because the connection you were on, you wouldn't be able to get the video streaming with enough what we call FPS or frames per second to where it would be smooth. It just made more sense for you to download the video, wait till it was done, and then you could play it all back on your computer locally without any sort of really stuttering or any technical issues there.
It worked, but it was a far cry from high-quality streaming video. For the quality of streaming to improve, videos needed to start up faster and be more reliable. And computer engineers were up to the challenge. They created a solution that would be called a content delivery network, or CDN for short, and it revolutionized the internet. Sandpiper, Interview, iBeam, and many other small companies were in the first wave of folks to experiment with the idea of a CDN. MIT applied mathematics professor and algorithmic expert Dr. Tom Layton was sitting down the hall from Tim Berners-Lee, the man who many refer to as the father of the World Wide Web. Berners-Lee posed a problem to the wider MIT community. Because of the way the web was built, congestion was bound to become an issue that held people back from speedy web browsing. Dr. Layton felt he could solve this congestion with math, using algorithms to intelligently duplicate and route content. He and a few colleagues got to thinking, if geographical distance was the problem, just get rid of the distance. Replicate the content and bring that content closer to people. This lessens the number of hops that computers would have to make to retrieve information and reduces the likelihood that any one server would get overwhelmed. Layton called his company Akamai, and it's still one of the largest CDN companies in the world today. But CDNs are just part of the puzzle. They help get the content physically closer to you, which helps it load speedily. But making that content look good is a whole separate issue. The secret ingredients for getting high-resolution streaming video are bitrate and compression. Bitrate, essentially, is just a measure of how much of a file you can transfer in real time, usually measured per second. Larger files are generally higher quality, but streaming large files takes more bandwidth. In video, bitrate is everything.
When we were on dial-up, there was just a limit to the amount of what we call bits that you could actually push through the wire to the consumer. It was literally a physical restraint.
And in the early days, bitrate was low, very low, mostly due to physical constraints. But even with those limits, internet video exploded in the early 2000s. And no platform took off faster than YouTube.
Lazy Sunday.
Ouch, Charlie!
Oh my God. Cheers. Stay in your seat.
Founded in 2005, YouTube democratized video making. Its platform was reliable for the time, but it wasn't without its faults. If you were on YouTube in those early years, you'll probably remember that watching a video went a lot like this.
All right, so here we are in front of the elephants.
Buffering was the absolute worst part of YouTube or any other streaming video platform in those early days.
Many times in the early days when you clicked play, you would have to wait 5, 6, 7 seconds for it to start up, and what was happening was you had to wait for enough bits to get from wherever they were to your location. And then many times we had rebuffering, which was, okay, you watch 10 seconds and it froze. You had to wait for the packets to come back to you.
There was a simple reason this was happening.
If you were encoding a video, let's say, for 300 kilobits per second, that's the only bit rate you were encoding it for. So if at any time while you were watching that video, your bandwidth dropped below 300 kilobits per second, the video would stop and it would rebuffer.
And with that realization came a simple but game-changing solution.
When adaptive bitrate came around, which is also something we call variable bitrate, content owners started encoding the video in 300K, 500K, 1 meg. So the point was, if you're watching it at 500K and your bandwidth degraded, instead of the video stopping at 500K, it would just reduce the bitrate to 300K but keep playing.
Or in simpler terms, when you're watching a YouTube video in high definition and your connection weakens, the player will automatically drop you down to a lower resolution to make sure that the video keeps playing.
The adaptive bitrate really improved the customer experience because the moment we could get rid of, as an industry, the rebuffering, what happened? Consumers watched more content. So adaptive bitrate, man, that might have to be on my top of my list of one of the best technology advances out there for the industry.
But having a solid bitrate is only one part of the two-part secret sauce for improving the visual quality of internet video. The other part is compression and decompression, referred to as codecs.
Here's the example I like to use for people who aren't technology savvy. It's like frozen concentrated orange juice. Okay, this sounds a little odd, but bear with me. So you get frozen concentrated orange juice, right? And it's very concentrated, but then when you put it in water, it expands and it's a larger volume. And video is kind of the same way. It starts off where you have to compress it, and then once you get it to the device that you're playing it back on, it decompresses it and it's better quality.
There are two main ways to do compression: lossy and lossless. Lossy compression reduces the file size with an obvious reduction in quality. Lossless compression reduces the file size without losing any quality. Lossless compression is the kind that video distributors like because it makes for a better user experience. It relies on redundancies in each frame to figure out where it can remove information. So, for example, in this shot from Avengers Endgame, the background doesn't change much, but Tony Stark moves around a lot. Instead of redrawing a new pixel for each frame each time, good compression allows for the pixels in the background that aren't changing much to be remembered and reused for the following frames. Only the portions of the frame where lots of movement occur, like Tony's face and arm, are redrawn with each frame. This results in a high-quality video at a smaller file size. For internet video to be as efficient and high quality as possible, all of these technologies have to work together. Here's how they do it. Let's say Netflix is preparing to release the newest season of Stranger Things. After it's edited and ready to be uploaded to the Netflix server, it has to be compressed. A team at Netflix works frame by frame to figure out the best method of compression.
They have an entire team over there that just looks at how do we encode video frame by frame, whether it's based on lighting, whether it's based on colors, all these different variables.
They compress that file into the smallest form it can be, while retaining the highest quality it can. They also encode it at lower bit rates, aka lesser quality, to give a few possible options in case your internet connection doesn't allow for the highest resolution, giving consumers flexibility to take advantage of adaptive bitrate. These files are also encoded into different formats that are specialized for every device the content could be played on.
It's not uncommon for many companies to have between 8 to 12 different encoding profiles inside the ladder so that you're constantly trying to get the best quality you can.
All of these files are then uploaded to Netflix's network. Seeing as Stranger Things is one of the most watched shows on the platform, they expect people to watch it as soon as it launches. In preparation for this, they ensured that a copy of the files for each episode is replicated across all the CDN servers they have strategically located across the globe. These servers act as a local hub for where the file will be stored for whenever a nearby consumer wants to retrieve it. The content is saved on multiple edge servers so that when a multitude of people try to access it, each individual can access the server that's geographically closest to them, resulting in the least amount of lag between when you click the play button and when the content actually starts playing. All of this happens in advance so that when you go to click that video, it loads virtually without delay. Of course, Netflix and other streaming services don't do this for every show. They strategically replicate the content they expect most people are going to watch. If you pick a show, however, that hasn't been saved on the server closest to you yet, it might take a few seconds longer to load that first frame because your device might have to request that content from a server that's much further away, potentially all the way to the main origin servers in LA. It isn't a significant amount of time, you'd probably barely notice, but thanks to you, that piece of content is now saved on a server nearby. If any other local consumer decides to watch the same movie or show, it would load virtually without delay. All of these technologies come together to deliver an experience that works almost like magic.
When was the last time you complained about the video quality on Netflix? Probably never, right? Or not in a long time.
Streaming video on the internet is objectively amazing. It seems like it got good overnight, but in reality, it's taken 25 years of experimentation, collaboration, and lots of learning how to get it to its current point. So, how does streaming change in the next 25 years? Expectations suggest that the industry keeps pushing technology forward in different ways. Possibly the biggest driver of technological growth might be the mobile industry. In the past few years, internet video has seen explosive growth in the mobile sector, thanks to apps like Instagram, TikTok, YouTube, and more. This continual shift means more of a focus on how to make mobile video content better. One way this could manifest itself is in better compression for higher quality videos at smaller file sizes. This would keep bit rates low while increasing resolution over a cellular connection. But in terms of watching content on your home TV, the next upcoming technological shift you may notice is content that loads even faster.
Today, as an industry, what we're trying to really improve on is the startup time, or what we call time to first frame. How long does it take before you see that first frame of the video?
Samsung and other TV manufacturers have released 8K TVs in recent years, doubling down on the idea that increasing the resolution will be a defining factor for the next wave of streaming technology. But not everyone feels that way.
8K, I think personally, makes no sense in the market in any way, shape, or form. The problem with 8K is it just doesn't add any benefit. For the type of content we're watching, the devices we're watching it on, it adds no benefit at all. People aren't going to want to replace their TVs again, all the other hardware that they have. There has to be a business logic behind this as a consumer. There has to be something that's driving it. I think where the industry is right now, as far as 4K being the max, purely from a resolution standpoint, I don't think it goes past there. I don't think it goes past 4K from an adoption standpoint because there just won't be a benefit.
The idea that we might be hitting the pinnacle of video resolution is a testament to how far the technology has come from its choppy, postage stamp-sized inception. So the biggest strides in the next 25 years of streaming might be found in making the rest of the experience as frictionless as possible.
It's not always about let's push out better quality. It's what really defines a user experience. We're also seeing some other technologies that are really providing some immediate benefit, like voice control. Now, voice control is not something you hear a ton about. I think a lot of consumers sort of just take that for granted. But it was interesting to have Hulu and Amazon on my stage at one time talking about consumers that were using voice control were consuming 3 to 4 times more hours of Hulu content than those who weren't using voice control. And that's an interesting point. Why is that happening? Well, simple, ease of use. Consumers want something that's easy. If it's easy, they'll use it more. I think the future is actually more voice control, more than it is a machine learning or AI.
While improving the quality and accessibility of streaming services on mobile and TV will be a priority in the coming years, we are starting to see that this is just the beginning of the streaming revolution. Industry leaders are already working on the next frontier of streaming: video games. The goal is to be able to stream entire games as easy as you stream a show on Netflix. Today, while most games allow for online social interaction, each game requires players to download huge files, like maps, characters, props, and textures, which are all stored locally on their system. Cloud gaming would unleash you from huge downloads and upload files of this kind. Though it would rely on similar underlying technologies, there are substantial hurdles that need to be overcome. Unlike movies, video games generally give each player a different point of view. So, not everyone is looking at the same images. Most games also allow players to make decisions that influence the visuals in somewhat unpredictable ways. Just with that, the technical complexity needed to pull off streaming a video game as opposed to a movie is exponentially greater. On top of that, gaming requires a super fast connection that minimizes any perceptible delay between when a player clicks a button and when that corresponding action happens on screen. Companies like Sony and Nvidia have been working on cloud gaming for years. Google and Microsoft have recently entered the arena with Stadia and xCloud. With their inroads in internet and infrastructure, there was renewed hope that the industry-wide revolution could be on its way. But this is just the start. If we are able to build a robust cloud gaming infrastructure, that could be a stepping stone in taking VR and AR technologies to the levels we've seen only in sci-fi movies. Imagine attending a concert from home, or getting a front row seat to the Super Bowl without having to leave your couch. This would revolutionize the way that we consume sports and entertainment. Beyond that, it could revolutionize the way we live. In school, instead of talking about how volcanic activity works, you could put on a headset and walk around a volcano in VR. Instead of going to school or work, we might just put on a VR headset and remote into our digital school or office. At a certain point, we could be in a Ready Player One-esque world, where there's a virtual oasis waiting for us with just the tap of a VR headset. All of that is a long, long way off. But the technology that we've built and refined to stream our favorite shows could one day be the backbone to a much greater system of immersive experiences. As we progress towards a future where video games, and potentially VR will dominate the internet landscape, it's clear that the next frontier for streaming will require a lot of new infrastructure and ingenuity. Fortifying access to reliable broadband internet will be paramount. Making these services affordable will be another challenge. But once we overcome these obstacles, streaming's full potential could be realized, a technology that will define our future.